Okay.
And our next speaker today is Dionysios Anninos, and he will teach us about topics in de Sitter space.
Okay, I'd like to thank the organizers for inviting me to participate in this school. It's very exciting for me to hear the talks of the other speakers and also try to share the subject that I'm going to talk about. Now, unlike the previous two talks, the subject I'm going to talk about is a subject with no experts, even though I'll try to motivate that it's a subject that should have experts. Oh, how does this work? Down. Okay. So I encourage people to ask questions during the talk, but let me start with the motivation, okay? The motivation comes from observations. It seems that by studying the photons in the celestial sphere and the small inhomogeneities of the photons in the celestial sphere, we are seeing some patterns that looks like a scale invariant type of noise. And people have tried to create models that produce such data in the sky and explain the cosmic microwave background radiation. And one of the prominent ideas to explain this has been the theory of cosmic inflation, which is a more sharp version of what the Big Bang is in the early universe, okay? So this is a theoretical idea that comes from studying a particular observational result. And the other object that we've been studying, again in the sky, even though we're at CERN, we can still look at the sky, has been the light coming from supernova, so exploding stars all around us that has been redshifted, providing us an example of the current phase of the universe, which seems to be expanding again. So this is called the positive cosmological constant phase. Okay. And so both in its earliest phase as well as its late time structure, the geometry or the shape of the universe seems to be that of an expanding, accelerating universe, which to some degree of approximation, and for the theorists, maybe we can take the idealized limit, we can just call the de Sitter universe. Okay? So this has been experiments, and I should emphasize that these have been experiments from the last 20 years. So the idea that we know what the shape of the universe is not a 100-year-old result, it's not 500 years old, it's a recent result about the shape of the universe. So it's an exciting result. Now, so let's put order 20 years here. Now, there's something else that we like to celebrate in the last 20 years, which has been another radical set of ideas. So let me call this the experiment motivation. So in the last 20 years, there has been another set of developments that has suggested that, very roughly speaking, because I suspect many people are not familiar with these kind of things, that that the continuum space of Einstein's theory of general relativity is some sort of emergent or collective phenomenon. Okay? So these are ideas that have been developed in the last 20 years, except the shape of the universe for which these ideas have been developed, instead of being expanding, have been the type of universe that looks like a deep potential well that pushes all of the matter due to the gravitational potential into the center. This is what people call the anti-de Sitter universe. Okay? So the challenge we have as theorists, just to give you, again, some motivation, is to understand whether these ideas, which I believe to be more general than the case of anti-de Sitter, can be used to understand things of this nature, the type of shape of the universe that we happen to live in. Okay? This is the general spirit of the research in these directions. And besides the obvious academic interest, it might be of actual practical interest in the sense that so far there's one aspect of this inflation theory which we haven't fixed, which is at what energies it might occur. So if it occurs at very high energies, where we need physics beyond the semi-classical limit, then we might need to complete our idea of semi-classical physics with something more general or more specific. Okay? So that's the motivation of why, I guess, I was asked to discuss this subject with you. So any questions about the motivation? Usually this is the easiest slide when someone is talking about this subject, because no one can question it. Okay, so typically, now comes the challenging part, which is that to gauge the level of knowledge of the audience when it comes to this subject. And my assumption is that, generally speaking, it's not a subject we're familiar with. So I'm going to try to take it from the start and assume a minimal amount of things. Now, there's a lunch between this talk and the next talk, and you can inform me whether the pace is too boring or too exciting. Okay. So, the strategy of the lectures is as follows. So first I'm going to talk about the basic features of the geometry and the symmetries. Okay? So we'll discuss what is this space looking like, how does it behave, and then we're going to think about putting some small fields both classical and quantum on top of this space viewed as a fixed background. Okay? So we'll just put a freely propagating field, maybe with some perturbative interactions, without affecting the geometry itself. So this is the no back reaction limit. Okay, then we'll discuss, let's see, right. This picture in terms of something that we're not very familiar with from quantum field theory courses, which is the Schrödinger picture of quantum field theory. Okay, so we'll try to recast the results we do in the operator picture in terms of the Schrödinger picture. Good. And finally, we'll talk about geometric fluctuations. No, let me write it like this. Now, let's see how far we get. But this should be roughly the first 1 or 2 lectures. And after that, the topics I'd like to touch on are something called the correspondence between the de Sitter universe and conformal field theories, just to express their general idea of what this is as an attempt to define non-perturbatively some sort of inflating space. And then I'll talk about the, let's see, what's called the static region of de Sitter. Okay? The words will become clear in a second, the word static. Okay. So that's the goal. It might be too ambitious or not, I don't know. But please keep me at the right pace, because if not, we will all be lost. Okay. Okay, so let's talk about the basic geometry then. So, as I said, even though the observations we make suggest geometry that is approximately de Sitter, we are going to idealize the situation and assume that it's exactly de Sitter, and see how far we can go with this idealization. Okay? This is something we often do in theoretical physics. It's like dropping the friction. Hopefully not all the physics is inside the friction term. Okay, so the geometry can be viewed as a solution to Einstein's theory of gravity, okay, with a positive cosmological constant added. Generally speaking, this is a term we can add to the Einstein theory that's a diffeomorphism invariant. What we cannot fix from general considerations is its value, okay? But this is something that we've measured. And the value today that we measure is peculiarly small, but non-zero nonetheless, and positive. Okay? So the most symmetric solution of this theory can be described in several different coordinate patches, but let me begin by expressing the solution in a coordinate system that covers the whole manifold. Okay? So here it is. This is the geometry. This is solving Einstein's equations at the classical level. And the coordinate t ranges over the whole real line. And this object over here is the round metric on the three-sphere. So the way to visualize this geometry then is that in the far past there is a large three-sphere. As time evolves, the three-sphere shrinks to a minimum but non-zero value, and then it starts to grow again. Okay? There's another way to write this coordinate system, which is useful if we want to consider the causal structure of the geometry. So I leave it as a homework exercise for you to show that we can write the geometry in a conformal way, such that the geometry is conformally equivalent to the Einstein static universe, which is just minus dt squared, the product of time times the round three-sphere, okay, times an overall conformal factor, where now the range of the time is finite. Okay? Now what this allows us to do is, allows us to express the conformal structure of the geometry in terms of a Penrose diagram, okay? In the following sense. Since in this conformal coordinate system the range of tau is finite, we can do a conformal transformation of the full geometry to something with a finite interval in time, okay? And the way we should read this diagram is that the constant slices over here are given by a complete three-sphere, where the poles of the three-sphere can be viewed as the two ends of this line, and every point on this line can be viewed as a two-sphere. Okay? So you imagine the three-sphere as a foliation of two spheres that grows and then shrinks again, and that is our complete Cauchy slice, okay, which has the topology of a three-sphere, and for this vacuum solution has the round metric on the three-sphere as well. Okay? Now, I can imagine further sending a pulse of light from the very far past all the way to the far future. Okay? And what will happen is that it will take the whole age of the universe, the whole infinite range of time, for the pulse to begin in one corner, in one pole of the three-sphere, and reach the other. Okay? Similarly, I can do the same experiment with a pulse coming from the other side of the universe. Okay? And this behavior of light rays in the de Sitter global geometry tells us that if I'm sitting along an inertial whirl line inside of the geometry, there is only a particular region of the universe that I can have an impact on, and there is only a particular region of the universe that can have an impact on me. Okay? So, of all of the de Sitter global universe, there is only a small region of space that is actually causally sensible to be discussed by a single observer. Okay? Now, to connect back to the original things I said about observations, let me discuss which observer has to do with which observations. Okay? If the cosmological constant that we observe today persists, given the fact that it's a non-diluting form of energy as opposed to the matter or the radiation, our universe will tend into something like this. And from this perspective, what we observe is a redshift such that eventually everything becomes arbitrarily dim. Those of you familiar with black holes have another way of describing that kind of physics, which is a horizon. Okay? So what de Sitter does from the perspective of an inertial observer sitting inside is that it produces a horizon. Typically, we associate horizons with collapsing matter. In this case, the universe is clever enough to produce a horizon by expanding space. Okay? So, there is a new type of horizon that we can talk about in this type of space, which is a cosmological type of horizon. Okay? On the other hand, if, like what happens in the theory of inflation, at some point the expansion ends instead of continuing forever, okay, we have a different kind of observation that we can make, which is a post-de Sitter observer sitting in their lab, like we do, looking at the light coming back into the universe that had been pushed out during the expansion. Okay? So this is a CMB type observer. Okay? Now, you may wonder at this stage which is the right observer to think about. After all, when we try to build some physics, we typically like to have a natural observer. In the case of asymptotically flat quantum field theory, this is the S matrix. In the case of the condensed matter theorist or experimentalist, this is the person poking holes with local operators. Okay? And indeed, these are the natural observables that we would have if our universe was either asymptotically flat or asymptotically anti-de Sitter space, where in the latter case, which is very much like the condensed matter case, we like to poke holes at the boundary of ideas and produce correlation functions. Okay? Unfortunately, in this case, we don't have that kind of observer. I'm going to postpone any philosophical debate about the observer until the very end and just do some calculations now. Okay? It's just too confusing. Okay. So the first set of calculations will have to do with the full expanding phase. Okay? And to make the symmetries a little more manifest, we're not going to work in the global chart of the manifold, but rather a local chart which has the following metric. This is the metric that cosmologists or inflationary cosmologists like to use, by the way. Okay? So, what does this cover from the global Penrose diagram? Well, it covers 1/2 of the Penrose diagram. And lines of constant eta, which is time, are given as follows, and on them is living the flat metric on R3 itself, okay? And lines of constant position are given as follows. Oh, and the future, which is the only asymptotic type of boundary that this universe has, is given by taking the limit eta going to 0 from the negative axis, okay? So what's nice about this coordinate system is that it will help us organize in terms of symmetries how to do calculations. So there are some symmetries here that are manifest. Well, I guess we can have an interactive moment now. Would someone like to share one of the symmetries of this metric, isometries of this metric? Yes, the translations, very good. No one said it, but probably everyone was thinking about it. So the translations are an obvious symmetry of this group, and in fact, all of the symmetries of the Euclidean R3 are symmetries of this geometry, and there is another one that's rather manifest, which is quite remarkable. Which is that if I take a point in this space and I multiply it by some constant, okay, and rescale my coordinates, and I also take my clock at that point and I rescale my time, then nothing has changed in the metric. So there is a dilatation symmetry that is manifest in this geometry, okay, given by taking x to lambda x and eta to lambda eta. The final symmetry that we have is not manifest, okay? But I leave it as a homework exercise to show that on the spatial coordinates, it acts as follows in the late time limit, okay? Oh, excuse me. So those of you familiar with the conformal systems will identify this symmetry as what's known as a special conformal transformation, and it's parametrized by 3 numbers, the vector b, living on R3, okay? And it constitutes the final 3 symmetries. Now we can do some detective work and try to guess what the full symmetry group is. So it is a symmetry group that has to have dilations, or SO1, 1 as a subgroup. It has to have the symmetries of R3 and the special conformal symmetries, okay? And also from the global geometry, because of the 3-sphere, it has to have SO4 symmetries as well. So what is the symmetry group of the de Sitter universe? Any takers? Okay, maybe I'm going too fast. Okay. Yes, very good. So it's SO4, 1, okay? So this is a nice group, and in fact, well, okay, it goes back to Freddie's issue with the 3 dimensions versus the 2 dimensions. Had UGM talked mostly about the 3D conformal field theory, I would have happily said, but these are the symmetries of 3D conformal systems. But I'll say it anyways, to repeat the joke from the morning. So the remarkable thing is that we have a 4-dimensional universe whose symmetry group, rather than the Poincaré group, is the 3-dimensional group of Euclidean conformal field theory. Okay? Now, we are accustomed to nature producing these kind of critical systems, but perhaps it's a novelty that the cosmology itself can produce a critical system for us. And the other point that might be worth emphasizing is that this symmetry, when we take the late time limit, so eta going to 0, and we see how it acts purely as conformal transformations of the boundary geometry itself. Okay? So the symmetry group, which acts on all 4 space-time points in the interior, as we take late times, becomes literally the symmetry of conformal transformations of the flat metric on R3. Okay? And this will have repercussions in terms of how fields behave at late times in a fixed de Sitter geometry. Okay? Any questions? Okay, if you want, we can do some parameter counting, just so I can slow down a little, because... So over here, we noted there were 3 parameters, okay? Over here, we have another 3, which are the 3 translations. Then we have the 3 rotations, so that's 9, plus the dilatation gives 10, okay? So from our considerations, we expect there to be 10 generators, and indeed, SO4, has precisely 10 generators. Okay? Good. What else do I want to say about the geometry? Okay. So now let's discuss having a small fluctuation on top of this geometry. Okay? And I'm going to discuss, for the sake of simplicity, the case of a massless scalar field. Okay? Now, part of the reason, as I said, to picking this example is because it's simple. But another part is that in the simple models of inflation, the object that carries the kind of fluctuations that we observe in the CMB is supposed to be that of a massless scalar field. So there's a phenomenological reason why we might pick this kind of action. And also, if we're interested in the fluctuations of the massless spin 2 particle in this theory, or the graviton, it turns out that the equations of that object are also essentially those of a massless scalar field. Okay? So it's a nice example to study for many reasons. Great. So, what to do? What are we supposed to do? We're supposed to solve the classical equations of motion. This is this is our exercise. And here we start to see why it was useful to pick the coordinates that we picked. In that we can further expand our space of solutions in terms of the Fourier modes of R3 for each constant eta. Okay? Now, in doing so, of course, we're making an assumption about certain normalizability features of the spatial profile of the field. But these are assumptions that we will live with for the time being. Essentially, we're assuming that the spatial profile of the field is square integrable with respect to the flat measure on R3. Okay? And I should make another remark about this, which is that the momentum k that we're doing our Fourier decomposition with respect to is not actually the physical momentum of the wave. Okay? This is an important point that will come back to us. The momentum k is actually a coordinate momentum. So would anyone like to guess what the physical momentum is at a given time, eta? It's k times eta. Yeah. Okay? So there's the scale factor that we have in the metric that scales our physical length so that the proper distance is delta x, the coordinate delta x, divided by eta. And so the momentum has to be the inverse of that, which is k times eta. Okay? Now this is important because oftentimes we need to keep track of large physical momenta. For example, if we're interested in calculating a loop, the UV cutoff should be in the large physical momentum region, not the large coordinate momentum region. Okay? Okay. But let's get down to business. Any more questions?
So is there a particular reason why you not choose minus eta times k? Wouldn't that be like natural?
Minus eta times k? Yeah. We can choose that. Would you prefer that? Okay. There's also some discrete symmetries here which take x to minus x and eta to minus eta, and we can fill the whole square. But yeah, I'm k, right, it's a vector. Yeah.
There's no cosmological constants anymore in the local metric.
Oh, here? Oh, sorry. I'm rescaling all of my coordinates so that they're dimensionless, and picking out the only scale in the problem to be outside the whole thing. This is useful because it allows us to just reinstate factors of L whenever we so need. And I should also say that the relation between the lambda, capital lambda I wrote in the initial action is given by plus 12 over L squared, where L is the Sitter length that I introduced when I normalized my geometry. Okay? Thank you for that question. Oh, excuse me. This is a 3, and the Ricci scalar is 12 or L squared. Okay, homework exercise is to verify whether or not I'm lying to you. Okay? Okay. Good. So let us continue trying to solve this equation. First, let's do some guesswork, and then let's try to fix it with an exact solution. So for large physical momentum, what might we expect of our solutions? So when we are in a large physical momentum regime, the wavelength does not feel the fact that the wave is propagating in a universe with a particular curvature. Okay? So what happens in that limit is that we might expect the wave to look as if it was a propagating wave in Minkowski space. Okay? So we might expect the wave-like behavior in the large physical momentum limit. What about in the other regime? Okay? In the regime where eta times k goes to 0. There we have to do a calculation, because this is the region where we're not used to studying the behavior of waves. Okay? So now let's stare at our wave equation, and let's put in our coordinates. Okay. Okay, so again, please correct me if I'm wrong, but I think this is the wave equation when we put in all of the coordinates. Okay? So in the small eta limit, the term over here will be seen to dominate over the momentum term. Okay? This is something that we can check self-consistently, okay? And the natural ansatz for solving this piece of the equation, or if we want, we can be a little bit more general here and include a mass term, just for those of you curious about doing the general mass term piece. And what we find is that the following ansatz, which is polynomial in lambda, with lambda equal to either delta or 3 minus delta, actually solves this equation in the small eta limit. Okay? So how does this work? When we take one eta derivative, we bring down one factor of lambda. Okay? Then we multiply by this eta squared, so then we have eta to the lambda minus 3, okay? Because we started with, we had eta to the lambda minus 1, divided by eta squared, eta to the lambda minus 3. Another derivative gives lambda times lambda minus 3 times eta to the lambda minus 4, which multiplied by the eta to the 4 gives lambda times the lambda minus 3 to the eta to the lambda, okay? So we've done something that seems to work. And on the other side, we have lambda to the eta to the lambda. And we have these two solutions for lambda, okay? Now, in terms of the physical mass of the particle, of course, this is just the mass of the particle itself. The reason I wrote it in terms of this peculiar notation delta has to do with the way that the representations of SO4,1 are organized, okay? So because the problem we were studying had this underlying symmetry of SO4,1, one is tempted to organize the solution space in terms of representations of SO4,1. And these are labeled more naturally by a scaling dimension or a number delta, rather than the natural parameter from the de Sitter point of view, which is the mass, okay? And what we can view this equation as from the point of view of the representation of the group is as a quadratic Casimir equation, okay? Now we can go to our mathematician friends and ask what is known about irreducible representations of SO4,1. Okay? And they will pull out the complicated books, and they will show us that the way that representations in SO4,1 are organized, if we further require them to be unitary, this is an aside on group theory, is that either delta has to be real and between 0 and 3, or delta has to be imaginary, but with the following specific form. Okay? 3/2 plus r nu, where nu is a real parameter. Okay? So these are the way to label irreducible representations of SO4,1. And now that we have a picture in terms of a particle in de Sitter, we can go back and think about what kind of particles these representations are describing. So just to end the footnote, if we solve delta in terms of the mass, we can express delta in the following way, where mu is the mass of a particle moving in de Sitter. And our representations come in two flavors. Either the mass of the particle is less or of the order of the de Sitter scale itself, in which case this root is real, and delta lies between 0 and 3. The reason delta has to lie between 0 and 3 is that we have to avoid the particle being tachyonic. Okay? So that's how unitarity manifests itself from the space-time point of view. And if we have a very heavy particle, okay, then we are following under the different representation, which is known as the principal series representation, which has the 3/2 plus r nu. Okay? So the physics of a particle in de Sitter has a natural group theory manifestation in terms of the unitary irreps of SO4,1. And for those of you who are familiar with ADS-CFT, a word of caution. These are not the unitary reducible representations we use in ADS-CFT. which would be those of SO3, 2. In those, there is never a complex scaling dimension to label our unitary reducible representations. The reason we have complex scaling dimensions in this context is because we are studying unitary reducible representations of the Euclidean conformal group, which is not what we do when we study radial quantization. Okay? Anyways, this was just a long aside for those of you familiar with ADS, because I don't want you to be confused by the complex number. Okay? Okay, so back to our master scalar, though. So what are the relevant values of delta for our master scalar field in the sitter? Okay, any takers? I'm going to wait it out. We're going to make this awkward. Okay, so if mu is 0, what values can delta take? 0 and nice, thank you. What? What's not allowed? Oh. Very good. Thank you for that. It is a subtle case, and we'll see the manifestation of your comment in a second. It has to do with the unwieldy infrared behavior of light fields in the sitter. So it's not a mathematical curiosity. Okay, so for a mass scalar field, then we're in the real delta range, okay, and we have either delta is 0 and delta is 3. In other words, when eta goes to 0, our field is approximated by, well, generally speaking, it would be a solution that behaves in the following way, but for delta equals 0 and 3, or what we have is a piece of the solution that goes like eta cubed times alpha, some piece that dilutes away in the late time limit, and a piece that is constant in eta that simply doesn't go away, but it becomes a smooth profile of the field. Okay? So now let's repaint this physical picture in our head. What we have then is a field which in the large physical momentum limit behaves as if it's a fluctuating wave moving around, as if it was happily living in Minkowski space. But as we stretch out the physical momenta to be in the deep infrared, the field has no oscillatory behavior, but rather freezes into some sort of a smooth profile. Okay? This is the transmutation of the field as it exits the sitter scale and enters the super horizon distances. Okay? And this is the reason why, even though the universe is expanding, light enough fields can still leave an imprint at very late times. Okay? You might have thought that they always dilute away and it's just always irrelevant. But this is the curiosity of light fields. This is the magic of inflation, in a sense. The same is true for gravitons. Okay, so now enough with the detective work. We can write down the exact solutions. So the exact solution is, in fact, and again, this is a homework problem for you to check. But they can be written in terms of the following two modes. Okay? Sorry. Let's write down the Fourier modes. So it is not hard to solve this wave equation exactly. In fact, it's not hard to solve it for general masses, but for light fields it's particularly simple. And the solution behaves as follows. It's a linear combination of two complex waves. Of course, for the classical solution, we need to take the real and imaginary parts of this thing. But soon we're going to quantize the field, and then we're allowed to consider complex solutions of the wave equation. And indeed, as eta, k eta becomes very, very large, the solutions look like oscillatory waves in a Minkowski type of space. And as eta becomes close to 0, the oscillatory piece of the wave function expands into an ordinary Taylor expansion, and we can check that the two solutions can be organized in terms of an eta cubed and in terms of a constant mode. Okay? So there we have it. This is the free wave in a fixed, free massless wave in a fixed de Sitter background. Okay, any questions? If there are no questions, let's proceed to ask how we should quantize this particle. Okay? So, when I wrote down the classical field, we saw that there are two solutions, and there has to be, because we need a full phase space worth of solutions, and we can view these two coefficients as coordinates living on a classical phase space. Okay? So what we would like to do when we quantize this field is elevate the coordinates of the phase space to operators acting linearly on some Hilbert space. Okay? And one way to do that is to declare this alpha and beta now to be operators. And these operators behave nicely under the conformal symmetry group. Okay? So we can organize our quantum field operator in terms of two operators, transforming under the representation delta or the representation 3 minus delta. And this would be one way to organize our quantum field, which is naturally expressed in terms of the late time limit. Yeah? So we've elevated the two profiles that act like conformal primaries to operators. There is a different way, which is of course equivalent up to canonical transformations, to quantize this field, which is to focus on the Minkowski region of the quantum field. Okay? What we are guided to do in this limit is introduce something like a creation and annihilation operator for the approximately oscillating Minkowski waves. Okay? So another way to write down the field operator, which perhaps is more along the lines of what we would do in flat space quantum field theory. Excuse me. Plus ik dot eta. Would be to say, well, when the wave is in the near Minkowski region, I have identified the pieces of my modes that look like positive and negative frequency modes, and I can introduce creation and annihilation operators that produce particles on a vacuum that is the Minkowski vacuum in that limit. Okay? Now, either of these things is a perfectly fine thing to do. It's just rewriting our field operator in terms of a different basis. And in fact, these operators over here, which are Hermitian, can be expressed in terms of linear combinations of A and A dagger. Okay? So alpha would be something like A plus A dagger, and beta might be something like A minus A dagger. Okay? So, what? Good. And, okay, so from the symmetry point of view, we may have felt that these are the natural modes to consider. In the context of cosmology or inflation, Instead, we focus on these field operators. Okay? Just to give you some context. But all of this has to do with a bigger question, which is how to select a natural quantum state for a quantum field in a de Sitter universe. Okay? So the reason we organize in Minkowski space in terms of creation and annihilation operators is that there's a natural perturbative vacuum state, which is annihilated by A, okay? And we can build a Fock space on top of this. And moreover, if we have a clustering decomposition behavior near the null infinities of flat space, where we build our S matrix, there's a natural Fock space that we can append to the boundary. This is not the situation here, right? So how to build a quantum state in de Sitter is a question that, as far as I know, we can only answer by making measurements, okay? And more ambitious theory might even produce for us the correct quantum state in an inflationary universe or something like that. But we don't have any such theory at this point. There have been interesting attempts, and we will discuss some, but at this point, the best bet we have is to fix the quantum state by making a measurement. And in the case of inflation, we have made a measurement, and so we know roughly what the fluctuations in this quantum state look like. Okay? So the quantum state that we will discuss will have the following properties. We would like it to be invariant under all of the de Sitter symmetries. Okay? This might be a reasonable thing. We would like it to mimic the Minkowski vacuum at large physical momentum. Okay? This is another requirement that we have of our state. And in doing so, effectively, we're fixing a quantum state which is annihilated by this A sub k's. Okay? This is called the Bunch-Davies wave function. Okay? And this is the wave function that we use to calculate fluctuations in the cosmic microwave background. Okay, so let's write that down. Very good. Now, one more thing. So probably it's time to go to lunch. But let me make a few more comments about the first requirement in fixing our quantum state. The requirement that we want our state to be invariant under the de Sitter isometries does not fix the state. There are many de Sitter invariant quantum states we can imagine building. And part of this reason goes back to the group theory that we were talking about before. Because the representations we are allowed to have are not just fields that transform with weight delta, but also fields which transform with weight 3 minus delta, also known as the shadow operators in the language of conformal field theory. But if we have an operator that transforms under delta and an operator that transforms under 3 minus delta, we can build a marginal operator that is invariant under conformal group by gluing them together and integrating over all space. Okay? So if we had a de Sitter invariant state, and we have these operators, delta and 3 minus delta, so the delta and its shadow, and these operators act non-trivially on the de Sitter invariant state we started with, we could imagine adding to this state an integral over all space of the operator times its shadow. And we might imagine producing, at least in the late time limit, states that are invariant under the full conformal group. So there's actually a whole family of de Sitter invariant quantum states that we might imagine building. Okay? So once again, for those of you familiar with ADS, this is a very different situation. The reason is that in ADS, one of the generators of our group is the Hamiltonian, and in a stable theory, we can define a symmetric quantum state as the ground state of the Hamiltonian. In the physics we are studying over here, there's a different situation because our background is time-dependent. We have no time translation symmetry, and thus no sense in which we can build the ground state of our Hamiltonian. Okay? And what this allows us, in effect, is to use those representations that weren't allowed in SO3,2 to build a huge host of de Sitter invariant states. And this is part of, going back to your question, this is part of the question of the unwieldy infrared behavior of late-time de Sitter. The delta equals 0 case is another case that looks, so what is something with 0 weight? It's the coupling of a marginal operator, right? So we could imagine, again, adding this marginal operator with delta equals 0, and if we're allowed to include it, then we build a plethora of possible de Sitter invariant states, okay? So this is a very tricky situation, even at the free level, where we're accustomed to being able to do things that we like, okay? Okay, so I guess I should end right now, and then we can reconvene after lunch. Thank you.
Thank you very much for this great lecture. Are there questions to be discussed before lunch? If not, then we meet again at 2:30, and lunch is, of course, in the cafeteria that direction. See you later.